Are there questions? Okay, let me begin. So last time we saw that when you quantize superstring theory, you have 4 different sectors, which are NS, RNS, NSR, and RR. So today we'll try to construct the spectrum in these theories. Okay, at least begin by constructing the spectrum in these different sectors. Okay, and let me remind you that this is being done in the analog of the old covariant formulation. Okay, later on we'll introduce the hosts. Okay, so here many things will become clear. Here you have to make some assumptions. Okay, just like we did for the bosonic string theory, right? For example, the normal ordering constant, okay, was not completely fixed, and we had to use, that was fixed eventually when you introduce the hosts. Okay, so there one more thing I should say is that if we use this relation, this is a supersymmetry relation. Okay, and so there is a similar relation for the transformation of psi. So this you can check. Okay, if you use the plus minus component is given by minus I epsilon minus psi minus now x mu is always periodic, right? Because x mu at sigma plus 2 pi is x mu of sigma. Okay. So that means that if psi mu is periodic, then epsilon minus has to be periodic. And similarly, if psi mu plus is periodic, then epsilon plus has to be periodic. Okay. But if this is anti-periodic, then this is also anti-periodic. And if this is anti-periodic, this is also anti-periodic. Okay. So epsilon plus is periodic in NSR and RR sector. Because NSR means psi mu plus is periodic, right? That's how we had labeled it, and epsilon minus will be periodic in RNS and RR sector. Why epsilon plus is periodic? Yeah, because this has to be periodic, right? This product has to be periodic because x mu is periodic, right? So whether epsilon plus is periodic or anti-periodic depends on whether psi mu plus is periodic or anti-periodic, right? And NSR and RR sectors are defined such that psi mu plus is periodic, right? Because the right sector refers to psi mu plus. Okay? And there, if R means periodic, NS means anti-periodic, right? So in the NS sector, psi mu plus will be anti-periodic, and that means epsilon plus also should be anti-periodic, right? Or similarly, RNS sector, psi mu plus is anti-periodic, so epsilon plus is anti-periodic. Is this clear?
So epsilon is dependent on the worldsheet coordinate, like when you go sigma
Yes,
plus 2 pi.
So from this we see that if you take epsilon to be rigid, right, independent of the worldsheet parameter, okay, then the supersymmetry is present only in the RR sector, right? Epsilon plus minus, if you take to be constants, then supersymmetry is present only in the RR sector. Okay? But as you have seen, there is a residual gauge invariance, right, that allows us to take epsilon plus to be a function of u and epsilon minus to be a function of v. Okay. So the rigid supersymmetry exists only in the Ramon sector. Okay? But if you consider more general versions of supersymmetry, right, which are also symmetries, okay, where epsilon plus is allowed to be a function of u and epsilon minus is allowed to be a function of v, okay, then in those sectors, in that more general case, we can have epsilon plus dependent on the coordinates, right? And that's how you make epsilon antiperiodic. Residual gauge. Well, last time we discussed this, that this transformation, the supersymmetric transformation, right, also is a symmetry if epsilon plus depends on u and if epsilon minus depends on v, right? Which are these are the residual gauge symmetries. Just as the conformal transformations are residual gauge symmetries in the bosonic string theory. Okay? So those are still there, but on top of that, you have these residual supersymmetries, which are where epsilon plus and epsilon minus are allowed to depend on u and v. Yeah, so we discussed last time, right, that you have to fix the covariant gauge, where you set the gamma alpha beta to be delta alpha beta and chi plus minus equal to 0.
So we are doing this NSNS3, this order is in like defining periodicity first for psi minus, then for psi plus.
Yes, exactly. So NSNS means it's psi minus is antiperiodic and psi plus is also antiperiodic. Right?
But like what I'm asking is 1 and 2 is psi minus and psi plus.
Psi minus is left and psi plus is right. Yes. So the R on the right means psi plus is periodic. Right? That's why this thing comes from. Is this clear? Yes. Constant epsilon plus minus. Yes, you can have. That's only half of the rigid supersymmetry, right? Only epsilon plus will be there or epsilon minus will be there. Yeah. But in the analysis, we don't have to really give some special preference to rigid supersymmetry, although it does play some useful role, right? One should think of these supersymmetry transformations in the same way that you think of conformal transformation in the bosonic string, right? There is, of course, rigid translation, right, where you translate tau and sigma, but more general symmetries are when u goes to a function of u and v goes to a function of v, right? And then translation of u and v are just special cases of that. So from that perspective, it's useful to think of this as part of a more general transformations, right, where epsilon plus is allowed to depend on u and epsilon minus is allowed to depend on v. Is it clear? So this will not immediately use, but later on we'll make use of this. So now we want to quantize this system. Okay. So to quantize, you have to do a mode expansion, right? So if you remember, we had done a mode expansion of x mu as x mu of tau plus sum over n okay, and quantized. So this gives you the x mu, p mu, and alpha mu n, alpha tilde mu n. Okay, and this is identical. So this, whatever happened in bosonic string theory, will also happen here. Okay, except that mu, we again run from 0 to d minus 1. Okay, d again is not fixed. You have to fix it afterwards. So this is same as in bosonic string theory. Now the fermionic action part of the action. Okay, earlier you had written it in the language of two-dimensional Gamma matrices, but today I am going to write in terms of components. So this will be given by I over 4 pi alpha prime. There is a simple exercise, okay, which requires that we take the Gamma matrices, two-dimensional Gamma matrices rho 0 and rho 1 that I wrote down, explicitly write that form, okay, and expand in components, right? And you will find that this is what you get. And from this again, you see that psi mu minus equation, for example, will give you delta minus del sigma psi nu minus equal to 0, right? Which basically means psi nu minus depends only on the combination tau plus sigma, right, which is V. And similarly, psi mu plus depends only on the combination tau minus sigma, which is U. But we want to quantize this system, so we want to do mode expansion.
Is there any reason or is it not possible?
Well, this is the simplest system, right? That's why you could have asked the same question in bosonic string theory. We wrote down the bosonic string action, right, which is a free field, right? We didn't allow any interaction among the x's.
This Nambu there, it's like the area of the.
Yeah. So here the point is, if you start with that, and then you say that you will supersymmetrize that action, right? Then this is the action that you have to write. Right? If you want to introduce interactions, you also have to introduce interactions among the x's. Right? So if you want the x's to follow from Rambo-Goto action, right, then yeah, this is a unique choice. Right? But there's a more general situation where you, for example, you can couple it to background metric, right? G mu nu of x del alpha x mu del beta x gamma alpha beta, right? So that will also have a corresponding interaction term in between the x's and the psi's. Okay, so this is a simplest case of flat space, right, where the x's have become free field and then supersymmetrization fixes the action for psi.
Besides the bosonic action on a curved background, you have to introduce xi interaction.
Yes, yeah. That if you want to do curved background, G mu nu of x del alpha x mu del beta x mu, yes, then there will be extra terms, right, which involves the extra coupling of bosons to fermions, and there are also 4 fermion coupling. Right? All those will come as part of supersymmetrization. Right? But that is known. I mean, what that action is known, but you have to do that.
Kind of introduces supersymmetric action at the level of polyacove, right? I mean,
yes.
But if let's say one wants to do it the Nabu,
yes.
At the area level, can we do it at that level also?
Yeah, you can. As this is what we discussed last time, not in the at least the polyacove level, right? Once you linearize Nambu-Goto by introducing this gamma alpha beta, right? Then you can supersymmetrize it. It requires adding 2-dimensional gravitational fields, the chi mu alphas, right? The chi plus minus alphas, and then you find that this has both 2-dimensional general coordinate invariance, but also 2-dimensional local supersymmetry, right? And then the while and super while, you gauge fix all that, and then you get to this covariant action. Okay, and that's what gives us to these extra constraints that you have to have T alpha beta equal to 0 and G alpha equal to 0, G alpha plus minus equal to 0. Right? So those will be the physical state constraints that you have to impose. Any other question? Okay, so now we are going to do a mode expansion of psi mu plus minus. So psi mu minus will be expanded as square root of alpha prime. Okay, this square root of alpha prime is just a normalization. We want to get rid of this alpha prime over here. times sum over R B at this stage it's just a matter of convention. Okay, you could have just declared B mu minus R as B mu R and then made it minus, but this is a convenient choice, as you'll see. Okay, this will make the B mu R with negative index as creation operators and B mu R with positive index as annihilation operator.
What's the spread where R runs?
Yeah, I'm going to do that now. Right. So the point is that R should belong to integer for R boundary condition and should belong to integer plus half for NS boundary condition. Right? Because if you want periodic, R should be integer. If you want anti-periodic, R should be integer plus half.
This may not cause confusion when you host.
When you introduce B host. Oh, B, this which B? Okay, it will carry an index. It's okay, I think. Yeah. So B, yeah, we can change the name, right? You can change the name as you please. What? It's not needed.
Convene is not necessary.
Okay. Yeah, but we will distinguish B from this by the index. So in terms of this, the action SF becomes half. Okay, so basically what we are going to do is that we do the sigma integral, right? That will give some delta function after you substitute. That 2 pi will cancel this 1 over 2 pi. Okay. So this will be I by 2 sum over R integral d tau. So notice that it's plus IR for both, okay? And that because 2 minus signs cancels. Here you had a minus sigma derivative, okay? But minus sigma derivative for psi mu minus brings down IR. Okay? And here you had this plus sigma derivative and that also brings down IR. So here I can rewrite this as I sum over R greater than 0. Okay, so all I have done is that I have rewritten the sum over R, which is running over all integers, into sum over R greater than 0, okay, and the 0 mode. Okay. Sorry, I by 2. Thank you. Okay. And then there may be constants which I'm not worried about, right? Because of the ordering. Okay. So from this you can construct the Hamiltonian, and Hamiltonian will, okay, maybe before the Hamiltonian, let me just say.
R sector or
No, at this stage you don't worry. So this is only in the R sector. Okay, otherwise you just write sum over R greater than 0, you can take to be integer or half integer.
Only RR sector.
This is, okay, in the RNS sector, for example, this will be there. Okay. In the NSR sector, this will be there. In the RR sector, both will be there. Okay, so now we go to the canonical formalism. Okay. So for this, we see that I B mu minus R can be taken is the momentum conjugate to B mu R. Now, whether you take B mu R as coordinate or B mu minus R as coordinate is up to you. Okay. But these are the canonically conjugate variables, because if you take the derivative with respect to the time derivative of B mu R, you get B mu minus R, right, with an I. This is from here. Okay. And similarly for tilde. So this gives you the commutation relation, that anti-commutation relation, because they are Grassmann variables. Pardon?
XP commutator.
XP commutator. Right? Yeah, so there is an I, sorry, there is an I, yeah, thank you. Yeah. Yeah, so I will cancel. Now for B0, things are a little more complicated, right? Because we can see that from this, that B0 is its own momentum, right? Because if you take the derivative with respect to delta B0 nu, you get B0 nu. Right? To raise although R by eta mu. So this means that it's a constant system for the B0. Okay, and you have to do some Dirac quantization. Because the coordinate and momentum are the same. Right? The momentum conjugate to B0 mu is B0 mu itself. Right? So that's why it's a constant system and you have to do Dirac quantization. So you can do that. Okay. But there is also a shortcut, okay, which I'll describe, but at the end we get the same answer. Okay. So the shortcut is that we write, so for B0, we do Dirac quantization. The shortcut is that let's define, say, B plus minus as 1 over root 2, B1 plus minus IB2. Okay? I'll just describe it in terms of two coordinates. Okay, but you can now in general. Let's suppose we define B plus minus as this is B0. Then the action can be written in terms of this. Yeah, 1 and 2 are like space-time coordinates, mu nu. Okay, I just combine 1 and 2 into a pair of complex b's. Okay, B plus and B minus, which are complex conjugates of each other. Then this action can be written as plus other terms, which you don't care. The terms involving B plus and B minus are this. Okay. How do you see this? Okay, that we have maybe it is half is not there. So if you take this combination, right, there'll be one where you get B01 delta B02. Sorry, B01 delta B01, right? That term is there here. Then you will get B02 delta B02, the I and minus I will give you 1. And then there are some cross terms, right? B01 delta B02 and B02 delta B01. But by integration by parts, right, you can show that those cross terms are cancel each other. Okay. So this is the same as this for mu nu equal to 1 and 2. Is this point clear? Okay. Just expand this out. Okay. And you will find that you get B01, B01 delta B01 plus B02 delta B02. Okay. Cross terms are 0. Okay. But now you see that now we are in business, because this means that we can take B plus or I by 2 B plus is conjugate to B minus. Right? Because if this is coordinate, this is momentum.
Dot means apart from 1, 2 direction, right? Apart from 1, 2 directions, others are included in dot.
Others are included in dot, exactly, right? But for each pair, you can do the same thing. As long as D is even, you can do this, carry this out. D will be even, so you don't have to worry, right? If it's odd, then you will go to Dirac, right? If it's odd, then you have to do Dirac, right? But at the end, it's the same thing. Because Dirac is designed so that when you can do the standard quantization, it should give the same answer.
So even if it was odd dimension, we could have mixed left and right moving modes.
Sorry, I didn't get the question.
Even for like odd dimensions,
Yes.
we could have mixed left and right moving modes to make
Left and right. See, left and right, yeah, maybe you can do left and right. Yeah, that depends on the boundary condition. As long as both left and right have Ramon, you can do that.
Yeah.
Right, but if left has Ramon and right has NS, then you cannot do that, right? Okay, so this tells us that b plus b minus is 1, 2. Okay. And b plus is 0. And this translates to b0, 1, b0, 1 equal to 1, b0, 2, b0, 2 equal to 1, and b0, 1, b0, 2 equal to 0. Okay, because you can write b01 and b02 in terms of p plus minus, right? And you can check this. Okay. So net upshot is that for the b0s, we have the anti-commutation relation. That b0 mu, b0 nu equal to theta mu. Pardon? Yeah, so if it starts with 0, right, we don't drop the I, right? You combine b0, 0 with b0 d minus 1 with just plus minus, right? Drop the I, right? And you can show it gives the same result at the end. Is that clear? Okay, so for b0, let me write. So for b0, 0, define b plus minus as b0 d minus 1 plus minus b0, 0. Okay, then no I. Okay, and then you can repeat the same. Yeah.
This B0 is owned by not Grassmann.
The Grassmann odd.
The Grassmann will B0 1 square.
No, these are operators. Grassmann odd numbers have b0 1 square equal to 0, right? But Grassmann odd operators need not have b0 1 square equal to 0. Right? Grassmann numbers commute, but operators don't commute. Grassmann numbers anti-commute, but the operators don't anti-commute, right? Just like the ordinary numbers commute, right? But Grassmann even operators don't commute. Okay? The same is true here.
The operator square is still 0, right?
No.
In the same level.
b0 1 square is 1 in this case. It's not 0. Yeah, usually you do Grassmann odd numbers, okay, or classical fields, but these are not. We are already doing canonical quantization, right?
Here also you can make raising and lowering operators and then make them square to 0, right?
Yeah, no, that is true. The b plus square is 0 and b minus square is 0. That b plus b minus commutator is not 0. Anti-commutator is not 0. See, it's like when you're doing path integral, right? Then everything commutes, right? You treat them as commuting numbers. That's what you do for Grassmann valued path integral. Right? But when you do operator formulation, right? Then even before you have heard about Grassmann numbers, right? Operators don't commute. Right? Same is true here. Operators will not anti-commute. Okay. The other thing is that Hamiltonian is easy to construct in this case. Okay, I should just say that you get the same result from Dirac. The Hamiltonian will be given by sum over R greater than 0. The fermionic part of the Hamiltonian. B0 doesn't appear in the Hamiltonian because since it's linear in time, right? Once you construct the Hamiltonian, these term just gets cancelled against the PQ dot term. Okay, this is generally true for linear system, right? Even the Dirac Hamiltonian doesn't involve time derivative, right? Time derivative of psi just cancels. Yeah, there is arbitrary constant, right? So this is all up to arbitrary constant. So plus constant. Okay. But the more important quantity is L0. Okay, and L0 tilde. So for L0, we fix the normalization in such that the bosonic part of L0 is exactly the same as what we had gotten for bosonic string. Okay, that's the way we fix the normalization of L0, right? After that, there is no ambiguity in fixing the normalization of the fermionic part because the action, we had just said that the expression for T mu nu, right, just constructed from Noether current, has an overall constant ambiguity. Right? But once you demand that the T mu nu is normal, that a bosonic part is normalized in the same way as the bosonic string theory, then that overall normalization is fixed. Right? Then there is no ambiguity in the fermionic normalization. So L0, in terms of these modes, one can show is sum over R greater than 0. Yeah. Let me write this. Yeah. So what I said is that we had written down the expressions for T alpha beta, right? So from T alpha beta, we can construct the expressions for L0, in fact, general ln L tilde, right? But T alpha beta we had defined as the conserved charge associated with translation symmetry constructed by Noether current. Right? The Noether procedure gives the conserved charge, but you can always multiply it by constant, and that is also conserved. Right? So overall normalization of a conserved charge is arbitrary, right? Any constant multiple of a conserved current is also conserved. But we'll fix the normalization, overall normalization, such that when you express ln's in terms of the oscillators, the bosonic part is identical to what we had in bosonic string theory, right? Which is what? Let me write it. We had some L0 for bosonic had sum over n alpha mu minus n alpha nu n theta mu nu plus other terms, right? With the zero mode term. Okay. So once I have said that this normalization is 1, right? That means I have fixed the overall normalization of T alpha beta. Okay. And this result that I am giving here, okay, is with that normalization. 1 or 2, I mean, depends on what you have to check.
You start with the alpha beta is the new.
Yeah, if I had done that, then the overall constant is 1. Right?
Bosonic our thing was just del alpha x mu del beta.
X, yeah, and then there's a minus half. Yeah. So then the overall constant is 1.
Your point that the Hamiltonian should at the end of the day be written as L0 plus L0.
Yeah, it will be, right? Hamiltonian, in fact, will not be important. Right? Hamiltonian is just a Hamiltonian never used. If you remember in the covariant quantization, the important constants are L0 equal to 0 and L0 minus tilde equal to 0, right? Hamiltonian is L0 plus L0, but that we had never used. Okay? That doesn't really play a role. Because ultimately the constant is T alpha beta equal to 0, right?
Yeah.
Which means separately you have to set ln tilde equal to 0, right? Hamiltonian is just one combination of the two. Any other question?
That's still not fixed the additive constant.
No, additive constant I have not fixed. I'll do that eventually. So now we have to build the Hilbert space. And this has to be done separately in each sector. Okay? So let's look at first NSNS. So we'll define this state K as before. Okay? So P mu acting on K will give you K mu on K. Okay, P mu is defined exactly in the same way as it did for the bosonic string. Okay, it's the zero mode in the expansion of X mu. And then we'll demand that alpha mu n by B. Okay, so B mu r's for positive R, we treat as annihilation operator, just like we did it for the alpha mu n's and alpha tilde mu n's. Okay, and the reason I do that is because we can see from the L0 expression, right? B mu r's lower the L0 eigenvalue. Right? B mu r for positive R. Okay, you can use using the computational relation, you can check that if you apply, say, B mu r on a given state, right, the L0 eigenvalue is lowered. Okay, this is like a Fermionic harmonic oscillator, right? It's this. So we take the K to be such that it carries the lowest L0 eigenvalue. Okay, that's why we demand that all the B mu r's annihilated. Okay. And then the general state is alpha tilde mu n to the power mu n. This is product over n mu by E. Minus where u mu n and p mu n can take value 0 or 1. And these can take any positive integer value. P mu n because we apply arbitrary number of bosonic and fermionic oscillators on this ground state carrying momentum k. Okay. And these cannot be more than 1, okay, because b mu minus r square is 0. Okay. That follows from these commutation relations. From this general commutation relation, right, you can see that if r and s are both -1, for example, right, then this condition is not satisfied, so you get 0.
That should be lower index should be R.
Yes, thank you. This will be R. This will also be R. In the NS sector, recall that R is running over half integer plus half values. Okay, so R can start from half, 3 half, 5 half, and so on. Yes, we have to do that same thing here. Yeah, right. So that the ln constant and the jn constants we'll do at the very end. Okay, so right now we are not worrying about that, about those constants. They will come eventually.
And skip it if it takes you on a tangent. But isn't the theory fixed by fixing the boundary conditions as well? Because if you think about the supersymmetry algebra, you do delta x to get some epsilon psi, like in terms of, and if you think of it in terms of mode expansion, so delta of alpha is giving you some combination of these, right?
Yeah, but so you are asking why are you summing over various sectors?
Yeah.
Yeah. So this is what I discussed last time, that the manifold on which the string is propagating, right, is not the one characterized by x, I, and psi tilde, right, but it's a quotient of that, right, which is that you take the space labeled by x, I, and psi tilde, okay, and there is a Z2 times Z2 transformation. The first Z2 just changes the sign of psi, second Z2 changes the sign of psi tilde. Okay. So this means that all the wave functions should be invariant under this transformation, because the space is actually quotient, right? So the wave function better have the same value at identical points, right? So let's say 2 points related by this Z2 transformation, right? Wave function should have the same value, right? So you have to impose a projection on the wave function. That is the GSO projection that we'll be discussing, right? The -1 to the f left to -1 to the FR should leave the set invariant. But at the same time, now when you talk about a closed string, right, a closed string can have both ends coming back to the same point in the original space. But you can also have a closed string where you start from, say, xi and go to x minus psi, right? So that is the other sector. So all of these states are closed strings, right, in this quotient manifold. Okay? And that's the justification as to why you want to add the different sectors. Right? So these two come hand in hand. The reason that you do GSO projection and the reason that you add various sectors is the same. Right? Because the space on which it's propagating is not the original space, but a quotient space.
This you have demanded.
Yes, this I have demanded. You can get a consistent string theory only on this space. Only if you are not on the original xi psi tilde space. Because you will get into tachyonic divergences and so on. Pardon? Yeah, but modular invariance comes much later, right? At this stage, right, we are simply saying that if we want a consistent theory, right, you have to make such identifications.
Then what does it mean to have the supersymmetry algebra which takes x to some specific combination of styles? And if I do a mode expansion there, how do I understand?
Supersymmetry algebra which takes x to a specific combination of size.
I can on these alphas, right?
On these alphas.
Expanded x.
Yes, true. So supersymmetry algebra, right? The expansion of J, that's what I discussed. The epsilons, right, in this case are also antiperiodic. Right? So supersymmetry algebra in this case will relate x mu, the alphas with integer modes with size with half integer modes, because the generators themselves carry half integer. Okay, this you can also see because the J alpha, right? Then we wrote down the expression for J alpha, right? And if you remember, it had something like psi del x, right? It is a product of psi and x. Okay? If psi is antiperiodic and x is periodic, then this is antiperiodic. Right? So its mode expansion will be also half integer moded. Right? So there is a conflict with supersymmetry algebra. You just have to remember that in the NS sector, the supersymmetry algebra itself is half integer moded. Okay, whereas in the Ramon sector, it will be integer moded, right? And then so it will relate integer moded x to x integer moded psi.
Maybe I can phrase the question this way: that if I think of these as 4 different Hilbert places, NSNS, NSR, RNS, and RR,
Yeah.
there are operators that take me from one state in NSNS to a state in RR or something.
Yes, there will be.
What kind of operators?
They will be spin operators. We will see what they are. Right?
They are not simple like X or psi.
No,
or
no.
like some of these modes,
Yeah,
right?
no.
Because these modes will keep you in the sector.
Yeah, they are not like that. Yeah, exactly.
And supersymmetry also does not mix the sectors.
Space-time supersymmetry will mix these sectors. Right? We will see how. World-sheet supersymmetry, no, it doesn't. Yeah.
So sector by sector, I have a supersymmetric Hilbert space.
Exactly. Yeah. Except that the supersymmetry algebra is different in different sectors. Right? In one case, it's half integer moded. In the other case, it's half integer moded.
So when we write the algebra, there will be like this one holomorphic part, anti-holomorphic part, and in the holomorphic we'll have half integer
Yeah,
and integer separately.
exactly. Half integer and integer separately. Right? So these modes are normally called GN, right? The ln, the analog of the ln's are the GNs, right? Which are the expansion coefficients of the J's. Right? J plus is Gn and J minus is Gn tilde. Right? And those n's will be integer in the Ramon sector and half integer in the NS sector.
And algebra doesn't mix.
Yeah, there are separate algebras in these different sectors.
Of that
Hmm.
that is labeling this case state, right?
Exactly. Yeah.
What is
B0 will that comes in Ramon sector. I'm right now doing NSNS. Right?
here it's antiperiodic, so
Here it's antiperiodic, so there is no B0. Is this clear? Okay. Now, in this sector, these are not all the states that you want, right? There will be physical state constant that comes at the very end, right? That will impose later after you study all the sectors. Okay? But before the physical state constant, there is a GSO projection. Okay? The GSO projection in the NSNS sector, right? GSO projection is the same. We have -1 to the FR and -1 to the FL. And you want -1 to the FR acting on a given state to be a state, because states should be invariant under this, and -1 to the FL acting on the state should be also the same state. So this projection is the one that implements that the wave function in the x psi tilde space is invariant under psi goes to minus psi and psi tilde goes to minus psi tilde. Right? That's the role of this GSO projection. So this changes the sign of psi. Sorry, this changes the sign of psi, and this changes the sign of psi tilde. Okay? So this basically says that -1 to the FR on B mu R is minus of B mu R -1 to the FR. Then -1 to the FL, B tilde mu R is minus B tilde mu R -1 to the FL.
FR is the number of fermions in the state, right? Like
Yeah, FR is roughly the number of fermions in the state.
after the action of the operator, right? Once you acted the GSO projector onto a state, then the -1 raised to FR should come out.
Yeah, but this is at an operator statement. -1 to the FR you think of as an operator. Right? It's a symmetry generator, right? FR is like a number operator. Right? Fermionic number operator. Okay, because every time you add a B mu, so what it says that every time you add a B mu, right, you change the parity of the state, right? Because you are applying an oscillator of psi mu, right? Psi mu plus. And that we know is odd under GSO, right? Because the symmetry itself takes psi mu to minus psi. Okay. So this means that if you apply it on this, suppose this is the state. I call this state, yes. You will pick up a factor of -1 to the power u mu r and you have to sum over mu and r. Right? Every time n -1 to the fr passes through this, right, you pick up a factor of u mu r, -1 to the u mu r, right? If u mu r is 0, then nothing is there, right? So then is another sign. If u mu r is 1, then that means there is a factor of b mu minus r. So passing through it picks up an extra minus sign. And the same thing is true for -1 to the f left. Every time you pass it through b tilde mu, it picks a minus sign. So you get sum over pr mu. Is this clear? So using that, you have to figure out what -1 to the fr on S is and -1 to the f left on S is. However, there is one ambiguity that you have to fix. And that ambiguity comes from the fact that this analysis doesn't tell you what -1 to the fr does on the vacuum state, K, right? Or what -1 to the f left does on the vacuum state. Is that clear? Because vacuum is not constructed by oscillator acting on something, right? It's just a state, right? So what does -1 to the fr acting on the state do? Pardon?
Since tachyon is in the even state, you just take the odd.
Yeah, okay, roughly that, but that's not the reason why you have to do it. Okay? So it turns out that the correct convention, okay, is that the vacuum is odd under -1 to the f left and -1 to the f right. Okay? Now this seems a little strange, right? The vacuum, see, K equal to 0 is supposed to be the SL2R invariant vacuum, right? And you would expect the SL2R invariant vacuum is invariant under everything. Okay? So this, for now, we have to just take as an ad hoc rule. Okay? But once you introduce the hosts, right, it will become clear why this rule is the correct one. Right? That once you include the product of this and the host sector, right, then basically you will see that what you are constructing, just like in the case of bosonic string theory, right, the host sector had a C1 on the vacuum, right? The host vacuum is C1 on the vacuum. So there is a hidden C1 that we don't see in the covariant formulation, the old covariant formulation. So similarly here, there will be a hidden operator from the host sector that we are not seeing here, right, which is odd under -1 to the f left and -1 to the f right. And that's the reason why it looks like here you have to make this ad hoc rule that the vacuum is odd under -1 to the f left and -1 to the f right.
But there's no just way of justifying this odd parity by just being in the old covariant quantization. I mean, without going to the course.
In the old covariant quantization, you have to basically go into the decoupling of negative norm states and so on. Right? Using that, one can show that the consistent string, the only way to form a consistent string theory is to declare these to be to have minus sign. Right? But as we saw in the many of these things which were somewhat ad hoc in the covariant formulation, right, become clear once you go to the BRST formulation, right? Once you include the host, the same will happen here. Right? So that's why I'm not trying to justify it in any other way, right? That right now we just take this as an assumption and proceed. SL2R vacuum in the matter sector you project out, right? Because this actual state is this SL2R vacuum in the matter sector times a state in the host sector, right? Which is not SL2R vacuum. Right? That has some additional operators, right? Which is odd under this -1 to the f left and -1 to the f right. Right? But that we'll see only when you do the quantization including hosts. Okay, right now we are just trying to do a shortcut to just get to the spectrum, right? What kind of spectrum we get. So rules which are ad hoc for now. Is that -1 to the f left on k is minus k, and -1 to the f right on k is also minus k. Okay. So GSO even states have sum over mu and r and sum over mu r. Sorry, this is not correct. I think I yeah, because these are of course all integers, right? So it couldn't have been integer plus half, but it has to be an odd integer, right? So that you can have odd number of products of -1, right? And that minus, so product is -1 and that cancels this minus. And
The part acting on that is will give you -1 to the power u mu r.
yeah, so it will give you -1 to the power u mu r. So if u mu r, sum over u mu r is odd, then it will become a next minus sign, and that cancels this extra minus sign, the vacuum. Is clear?
DSO even has to be, DSO even states have to be invariant when the action of -1 to the FL and FR separately.
Yeah, acting on a state equal to the state itself. Right? Because this is a statement that the wave function should be invariant under psi plus goes to minus psi plus, and psi minus goes to minus psi minus.
And we just forget about GSO odd.
Yeah, we just forget about GSO odd. Those are not part of the spectrum. So when you impose a physical state condition, right, you have to only work with GSO even states.
Supersymmetry and all will in general mix GSO odd and even state.
Space-time supersymmetry. No, not GSO odd and. Yes, it is true. Yeah, we are comfortable with it. I would just, at the level of formulation, right, wall-sheet supersymmetry is there, but the generator is odd, right? So it will mix GSO odd and GSO even, right? But this doesn't cause any problem in making the projection, because imagine that we want to project into physical states, right? ln acting on the state should be 0. That is straightforward, right? It takes GSO even state and makes it into linear combination of GSO even state, which you want to set equal to 0. Gn, which is the mode expansion of the supersymmetry generator, okay? It takes a GSO even state and makes it into a linear combination of GSO odd states, right? So there's no mixing between GSO odd and GSO even, because Gn is GSO odd, right? So you have to demand that linear combination of the GSO odd states is 0.
Should come out.
For physical state, it should come out, right? But this state, this spectrum now is not physical, right? You have to impose the analog of the ln acting on state equal to 0 condition and Gn acting on state equal to 0 condition. Okay? So those are extra constraints that you have to impose on this state, which you have not done so far. And just like in the bosonic string theory, we have to impose ln acting on the state equal to 0 for positive n. Here also you have to demand that gr acting on the state equal to 0 for positive r.
Even in the remaining part of it, even after GSO projection.
Even after GSO projection, exactly. Okay? Because GSO projection is an extra ingredient that comes in superstring theory, but the physical state conditions are still have to be satisfied.
Constraints have got to be set.
No, constants have not been put yet. Yeah, GSO projection is just saying that it's moving in this quotient space.
The supersymmetric, the physical condition, the J acting on the state is 0. That has to be imposed, or that is.
That has to be imposed.
But as you said, J on even is like odd.
Yes.
Which under GSO projection is anyway 0, right?
No, it's not 0. We have just removed those states, right? Now you have to demand that J acting on the GSO even state is 0. See, those states you have not set equal to 0, right? We are simply saying that those states are not part of the spectrum. But G acting on GSO even state gives you a linear combination of GSO odd states. And that linear combination of GSO odd states must vanish identically.
But on the once that has been done, we'll be left with some set of GSO even states with some specific values for these matching conditions and all those things. But in that space, there is some symmetry, right, which is linking some bosonic fermionic states in some sense. I mean,
No, in the GSO even states, Gn takes a GSO even state to a GSO odd state. Yes.
that generator is now pointless.
Exactly.
Well, not pointless, but something has happened.
But you have already imposed that, right?
I mean, for instance, I could have added two supersymmetry operators to bring it back to even, right?
Yes.
That may still remain.
That may still remain,
That
yes.
should give rise to some sort of.
Yeah, but typically commutator of two anti-commutator of two supersymmetry generators is Ln. Is a linear combination of Ln.
Keep it in that.
Exactly, yeah.
But there is some space-time supersymmetry which will link.
Space-time supersymmetry is quite independent of all-sheet supersymmetry, right? It is needed eventually, okay? But space-time supersymmetry hasn't appeared yet because you have not even seen any space-time Fermion, right?
Yeah, but I'm just saying, after all this is mind, there's still some symmetry linking all these states, right? Some analog, I would call it supersymmetry, but.
Just like there is a Virasoro algebra linking the various states, right?
Yeah.
But once you impose the Virasoro constraints, right, then a generic Virasoro generator will either annihilate the state or will take you out of the physical subspace, right? Except the ones which are the spurious states, right? Pure gauge states, right? Where you apply L minus n, right? The state is still physical in the sense that it's annihilated by all the Ln's, and those states are what we normally identify as the pure gauge states. Null state. Right? So the analog of all of those will be here. Right? You can get null state by applying G minus by G minus R's.
This condition will set Ln for n positive equal to 0 and Gn for n positive equal to 0. Then we'll get some physical states, and if we add on those states with some Gn, G minus n say, then that will give us 0 trivial.
Yes. That will give us 0 trivially. No, it will not give us 0 trivially.
All the states, physical states, these are GSO even.
Yes. Now you apply G minus n, right? This state is not part of the spectrum. You have to remove it by hand. It will not give 0 identically. Either these states are not to be included as part of the spectrum, right? The constant comes by applying Gn with positive n, right? Gn with positive n will generate a linear combination of GSO odd states, and you have to make sure that that state is 0, right? So that gives a constant on the original state itself, right? If the original state was a linear combination of basis states, then you have to adjust the coefficients of the linear combination such that G plus n acting on this gives you 0. A single G minus n acting on such a state is of no use, right? But imagine that you can apply two G minus n's, right? G minus R1, G minus R2. And that state satisfies the condition that all the Ln's and Gn's with positive n are annihilated. Okay? Then that will be a null state. So the space of states in which are physical is always in the GSO even sector. Okay? But when you demand that the physical state condition, that Gn acting on a state equal to 0, okay, doesn't mean that it identically is 0. Right? You have to check what Gn acting on the state does and set it equal to 0 explicitly.
That's what we did in bosonic also. So it was
Exactly.
the case.
Yeah, in the bosonic case, the point is ln acting on the, there was a GSO projection, right? So ln acting on the state was also part of the original spectrum. Here, Gn acting on the state would have been removed, right? That space, subspace is not there. But nevertheless, this constant you have to impose. Any other question?
So all states in a computation that we are getting, which we have to set 0
Yes.
for consistency condition, that will be like that will modify the physical subspace itself. Like how are we?
It will put one constant on the physical subspace. It will put more constant on the physical subspace.
This becomes naturally 0.
Exactly. That's right. Okay. Just like we check that if you have a given level state, right? You can, if you apply ln for a sufficiently large n, it is automatically 0. Right? Same is true here. If you apply gn with gr with sufficiently large r, it will be automatically 0. Okay? So you have to just check the appropriate combinations, which are not automatically 0. Those you have to impose explicitly.
Define level separately for the
Level you fix by L0 and L0 tilde eigenvalues. Right? Because the way we define the levels, GR will have L0 equal to minus R. Right? Just like LR had L0 equal to minus R. Any other question? So this constant you are going to impose eventually, right? Not now, right? First you have to study all the sectors and see what kind of states we get. So the lowest L0 state for given K. Any guess what it will be? Yes, even, yeah.
Just one.
Hmm.
But G is also
What? No, G, forget about ln as physical state condition. Just
this.
Some kind.
one alpha one.
No, 1B you will have to.
Oh, 1B is also.
1B, yeah.
1B, 1B.
1B, both of them.
Yeah. 1B, 1B tilde because B's have half integer modes, right? So B have, there is a B minus half, right? If you use alpha, you have to go to alpha minus 1, right? That has L0 eigenvalue 1. Right? B minus half will raise the L0 eigenvalue by half, right? So it's B mu minus half. On K. Because you need odd number of B's, right? So you need at least one B and one B tilde in any case. Right? So why use anything else, right? Because you just use this. Okay. So this is going to eventually give the graviton-dilaton antisymmetric tensor field. These states will eventually give the graviton-dilaton antisymmetric tensor fields of fermionic string theory, of superstring theory. Karl-Bromon will be antisymmetric combination of mu nu. The metric will be the symmetric combination, and the dilaton will be the trace. Okay. So in the bosonic case, if you remember, it was alpha mu minus 1, alpha tilde nu minus 1 acting on the K, right? Those are the states which gave graviton, dilaton, and Karl-Bromon field. Here is the B's.
Geometric meaning for G, what is the B or the capital B?
That's, yeah, there, I mean, you can give a geometric meaning, but you just think of this as a tensor. Right? Just like in this question, you could also ask in the bosonic string theory, right? It's just one field in the theory. Sometimes people interpret this as a torsion, but you don't need to do that.
These states are inherently antisymmetric. How does it have?
No, this is B and B tilde, right? They anti-commute, but mu and nu are independent indices, right? So all that you are saying is that the symmetric or the antisymmetric combination will be metric and symmetric combination will be B, right? But we are just going to symmetrize in mu and nu, right? Then there's a confusion. If you take zeta mu nu, right? Then the zeta mu nu, the symmetric part of zeta mu nu will give the metric, and the antisymmetric part will give the Kalber bond. Because in terms of polarization, there is no confusion, right? Because polarizations are always C numbers, right? They are always Grassmann even.
I think that if you take a symmetric zeta mu, this just vanishes.
No, it will not vanish. B and B tilde are different. Yeah, zeta mu nu is an arbitrary matrix. Yeah, it's a two-rank object. Yeah, general two-rank object. See, you could have asked that you had alpha mu minus 1, alpha tilde nu minus 1, right? But that gave both symmetric and antisymmetric part, right? Even though the alpha and alpha tildes commute. Right? So because these are different oscillators, right? The zeta mu nu doesn't have an extra symmetric condition. Is clear?
So the physical state constraint will give the case condition.
Yeah, so the physical state condition will basically tell you that this is massless, right? But that is going to come later. I am not going to do that today.
That will come from the G then.
From the basically L0. L0 acting on that, you have to fix the normal ordering constant, right? The normal ordering constant is such that it will be k square. Right? L0 will pick up, see, L0 picks up a half from here, right? That constant is going to cancel that half.
And then you k square equals 0.
Yeah, then you get k square equal to 0. Okay, so these are described later when you actually impose the physical state condition. But let's look at the Raman sector. NSR. Okay, so which means the B mu R have R in Z. They are integer moded. No, the right side is Raman, right? Right in my notation is B. So for the non-zero modes, it's not a problem because we just declared B mu minus R creation, and B mu R are annihilation operators. For R greater than 0. Okay. So we demand that the B mu R's for positive R annihilate the vacuum. Okay, so that part, that discussion is similar to what we had here. The problem comes from the zero modes. Right? So the zero modes have this feature that B0 mu, B0 nu is eta mu nu. So that means B0 1 square is 1, right? So you cannot demand that B0 1 annihilates the state, right? Then it will be inconsistent with B0 1 square equal to 1. So the question is, what do you do in this case?
Earlier that was for the innocent sector.
Yeah, so for P mu, right? For P mu, we have to do something different, right? The zero mode sector gave this K, right? Because we quantized it as a free boson, free particle, right? Wave functions were e to the I k dot x, right? You couldn't use oscillators. Right? Here you have a similar feature, but these are fermionic modes. Okay? So it doesn't make sense to assign Grassmann or momentum, right? Okay, so you have to do something. Okay? So one way to see what we should do is to note that this algebra, right, is like the Clifford algebra, right? Up to a normalization, right? This is the Clifford algebra, gamma matrix algebra in 10 dimensions. And we know that the representation of the Clifford algebra are spinor states. So we expect that the vacuum, right, in this case, will not be a unique state, but it will be a spinor representation of SOD, or SOD minus 1, 1. Is this point clear?
Could have just gone to the B plus minus.
Yeah, that's another way, right? It's the same. I'm going to do that, right? Going to the B plus minus.
Why SOD minus 1 rather than SOD?
SOD minus 1, 1. That's the full
Okay. Yeah.
Yeah. So it's a spinor, it has to be a spinor representation of SOD minus 1, 1. So if we use B plus minus, right? And similarly for everything else. Then we saw that B minus B plus this was what? 2. Because there will be B1 with B1, right, which will give you 1, B1 square, and then IB2 with minus IB2, that will also give you 1. So B plus B minus will be 2, and B minus square is 0, and B plus square is 0. Pardon? Sorry, P0, thank you. Yeah, but now we are trying to find the representation. It is similar to what we did last time. What was there? Is it okay? Some normalization.
Order of plus B minus. But
Yeah, that doesn't matter because it's anti-commutator, right? Okay, so this means that we can take the ground state K to be labeled by say minus, such that B minus acting on this equal to 0. You cannot apply B minus again because B minus square is 0. But B plus B minus K, this is not 0. Okay. So this we declared as K plus. So ground state becomes twofold degenerate. See, the B0s all come out with the L0, right? Or with the Hamiltonian. So ground state becomes twofold degenerate. B plus acting on, sorry, B plus acting on K minus, thank you. B plus acting on K minus. Every other state that we can get by applying B plus and B minus is expressible as a linear combination of K minus and K plus. Okay? If you apply B plus on this, okay, you just pick up the commutator, right? B plus B minus, and then you apply B plus acting on this. Sorry, if you no, B minus acting on this is 0. So B plus on K minus is already you have found, right? K plus, so it's not a new state. And B minus acting on K plus will give you B minus, B plus, K minus. And this is the same as K minus. Or with minus K sign, right? Because B plus B minus, you can write it as the anti-commutator and minus B minus B plus B minus. Anti-commutator gives you, anti-commutator gives you K minus. And then B plus B minus on K minus is 0 because of this condition. Pardon? Oh, 2 is there, okay. 2 is there. So the upshot is that if we have a pair of the zero modes and if you quantize it, right, the minimal number of states that we need is 2.
So you see that in the spinorial representation, there is a 2 to the power of lower d by 2 and all.
Exactly, right? So total number of states, so you can do it for d by 2 pairs, right? You'll have d by 2 pairs. So total number of states will be 2 to the d by 2. So total number of states is 2 to the d by 2. Pardon?
Which was just 1.
Which was just 1 in the NS sector. Right? Instead of 1 state in the NS sector, you will have 2 to the d by 2 states.
Usually 2 is to 4 of d by 2, right? For any d.
2 to the power?
4 of d by 2.
Yeah, so d is even in this case, right? In anticipation, the d is even, so it's 2 to the d by 2, right? And I'll assume that d is 10, okay, and so it will be 2 to the 5, 32 dimensional space. But only half of them are GSO even. Okay? Because imagine that K minus is GSO even. Okay? B plus is GSO odd, right? So if K minus is declared as GSO even, then B plus acting on this will be GSO odd. Is it clear?
Because I mean, under 1 minus to the power f just change.
Exactly. For every B, the minus 1 to the F will change sign. Okay. So for D equal to 10, we have 32 states. Only half of, only 16 are GSO even.
The counting code I mean, half is fine, but it does not matter which half it is, right?
It will not matter at this stage, but eventually it will matter. For this case, yeah, it doesn't matter which half you are taking.
What is the parity for K?
For K minus, yeah, this is like that, right? Yeah, that we have, if we declare that K minus is even, then the B plus acting on K minus is odd. That is gone.
But that is also unambiguous fixed when we introduce those.
No, it will not. This is the difference between type 2 and type 2B. So it will not be unambiguously fixed.
Type what?
Type 2 and type 2B string theory. Right? So what are these two choices, right? Which half we keep? Okay. So it turns out that this choice refers to which of the two spinor representations of SOD minus SO91 we choose. SO91, right, this 32 dimensional spinor representation is not an irreducible representation. The irreducible representation is a 16 dimensional representation, right? Because it has two spinor representations. Okay, one is with chirality positive, the other one is chirality negative. Okay, so these correspond to positive chirality and negative chirality spinors. Yes.
So it will K minus K plus for each pair of B plus minus because you have all this B views.
Yes.
In pairs of them.
Yes.
Pairs you have K minus and K.
Exactly.
Each of these pairs, you can use one of them to be its positive.
Yes, that's true.
Large choices for
True. But those choices are not all independent, right? Because you see, suppose you take this k minus and then the next one is also take k minus. Okay. Now you can apply b plus from the first one and the b plus from the second one. Yeah. Take 4 zero modes, right? For the first pair of zero modes, you have a minus state and a plus state. Imagine that the minus state is the GSO even state, right? For the second set, again you have a minus state and a plus state. Let's suppose that you have a minus state and a GSO even. You cannot apply a single b plus. Right? But you can take the b plus of the first sector and b plus of the second sector. That is GSO even. Right? Take minus minus or minus minus prime, right? Take minus minus prime, okay, and apply b plus prime. Right? Or b plus prime corresponds to the other two zero modes, right? This one is GSO even. If minus minus prime is GSO even, this one is GSO even. Right? So using that, you can show that there is only two choices, right? Because all you are doing by making a different choice is that you are postponing the whole set doesn't change, right? As a whole set, it's just two different sets that you can choose. Right? Even though where you start may differ.
I should then add the label, like 5 minus or pluses.
Yeah, this is -1, -2, right?
But the actual state will be the vacuum.
Actual state will be the?
Will have 5 labels. Right?
Yes, indeed. Indeed. So plus, 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 plus will have one, will be one state.
That is like the 5 states.
Yes.
I have choices. I select any one of them.
You can choose any one of them, right? But now the GSO projection will tell you that the total number of classes should be, say, even.
Yeah.
Right? Something like that. Yeah. So make it half. Okay, but after that, right, so there are these two different classes, one where the total number of classes is even and where the total number of classes is odd. Right? After that, you can go between them, right, by applying these, the B zeros. Okay, GSO even B zeros.
So this GSO even, so it is like choosing a chirality as well. Is it the same?
It's choosing a chirality, right? So when you make a choice, you are choosing a chirality. Exactly, right? So you can choose positive chirality or negative chirality, right? So for NSR, we can choose positive chirality or negative chirality. As to whether you are taking all pluses, whether you are taking even number of pluses, plus states, or odd number of plus states. No, this is space-time chirality. Because now you are talking about what kind of spinor representation of SO d minus 1 oil. Right? So this chirality refers to space-time. Yeah, like gamma 11.
See this from the space state picture of this idea that GSO is like going from x psi to x minus psi.
No, see, that is world sheet, right? This is in space-time. So a priori, these have nothing to do with each other. Right? So you can't see it from there. You just see it by thinking of this as a Clifford algebra. And all you are doing is that you are constructing representations of the Clifford algebra. Right? Which you know have two inequivalent representations, right? Which are positive and negative chirality.
The target space picture will emerge only after you have done the GSO projection. Or can you talk about GSO projection in some abstract target space?
No, this is GSO projection is at the level of the world sheet, right? It's not at the level of the target space. You have to, yeah, so target space interpretation you get only after GSO projection.
Yes, and there you can see this, what you were saying a while ago, this difference between 2 and 2b.
Yeah. Right, so I'll describe the difference between 2 and 2. Okay. So now the point is that the ones that you have projected out from the ground state, right, are not all useless. Right? Because imagine that you have a GSO even ground state, right? Then that is an allowed state by itself, right? Provided it satisfies the ln and gn conditions. the GSO odd ground state is not allowed, but you can apply even number of B minus R's on that. Sorry, odd number of B minus R's on that, right? That will be even. That will be already in. No, now non-zero oscillators, non-zero mode oscillators, right? Take a GSO odd ground state and apply the non-zero mode oscillators, right? That will be an allowed state. From the GSO even state, you have to apply even number of non-zero mode B's. Right? So this way you can construct the whole spectrum.
Considering the GSO odd states, choosing the vacuum to be GSO even.
No, in this case, there are two kinds of vacuum, GSO even vacuum and GSO odd vacuum. If you are just looking at the vacuum state by itself, then you have to pick the GSO even one. But you can decide to take the GSO odd vacuum and apply odd number of B mu R minus R's, right? The non-zero modes, odd number of non-zero mode B mu. That will be GSO even again.
The whole spectrum, the lowest state, I will not have the GSO odd vacuum.
Exactly.
In this case, I can have non-zero, odd number of oscillators acting on the GSO
Odd vacuum, that will be an allowed state. Right? Because all you are demanding is that the total states will be GSO even. Is clear? Okay. So this is the way we will build the spectrum.
Can you tell about this thing that this 32-dimensional representation of SOD minus 1, 1 is reducible?
Yeah, the SOD minus 1, the SO, let's focus on SO 9, 1. Okay. It had 16 and 16 prime representation. They are opposite chirality. Right? And in the language that I am describing, right, as Rishabh was saying, we should label the states by 5 labels, each can be either plus or minus, right? Because you can take either the minus or the plus that you get from applying the analog of the B plus. Okay. So a state is labeled by these 5 different labels, each carrying 2 values, right, plus or minus. And then the irreducible representation are obtained by requiring that the total number of pluses is even, that's one irreducible representation, and total number of pluses is odd is another irreducible representation.
So it's just the representation theory argument that 16 and 16 prime are 2 different representations, so we can choose this.
Yeah, it's a representation theory argument, but it also follows from GSO projection, right? Because you only project half of them. Right? Then you cannot include all of them, right? So the GSO operator, right, takes 16 of them and converts to other 16. Right? So one of the 16s you have to eliminate. Right? Which one you eliminate is up to you. Right? That fixes what the chirality of the state is. Right? You can choose positive chirality state, ground state, or negative chirality ground state as your allowed state.
So we can choose 16 or 16 prime.
Exactly.
The RNS, if we choose 16 or 16 prime, that would give us this 2.
Yeah. So the point is, so in the NSR sector, right, you can choose 16 or 16 prime, right? That is on the right moving side, right? Once you have done that, then on the RRA, you have no choice, right? For right moving, you have to choose that 16. Suppose I have chosen 16. But independently of that, in the left sector, when suppose it's RNS, right? Then the left sector is in the Raman sector, right? There again, you have a choice of 16 or 16 prime. Okay. And so now, the 2 inequivalent choices are when both sides you choose 16. Right? If you choose 16 prime on both sides, then they are equivalent. Then that's equivalent. Okay. But if you choose 16 from one side and 16 prime on the other side, okay, that gives a genuinely inequivalent string theory. Okay. And that is the difference between type 2 and type 2b. Right? In type 2b, we choose the same space-time chirality, ground state, in both sectors. In type 2a, you choose opposite space-time chirality ground state in the 2 sectors.
Target space is like taking 2 chiral phenomena or instead of 1 chiral, 1 anti-chiral.
Exactly. That's right.
Also, just to be sure, in this 10-dimensional picture, in target space, the spinor representation is still 32. Like gamma matrices are 32 dimensional.
Yes, but the Lorentz group, the representation of the Lorentz group is 16 dimensional, right? Because Lorentz group involves quadratic combination of gamma matrices. Right? That's why acting on a left chiral spinor, it always gives you left chiral spinor. Right? Even though the gamma matrices takes a left chiral spinor and converts it to right chiral spinor. Right? That's why they are GSO odd in this language.
So RNS case, you cannot have anyway cannot have equivalent spectrum on both sides, right? Because I mean, if you have NS, then the modes are different. Right?
Yeah. By equivalent, I meant whether you choose to keep the chiral or the antichiral part in the Raman sector. Right? So in the NSR, right? Suppose you have decided that you will keep the chiral ground state. Right? In the RNS, so that gives you a set of fermions, right? Because they are spinor representations. In the RNS, you may decide to keep antichiral ground state, right? Then from the ground state, you get one set of chiral modes and another set of antichiral states, right? In these two different sectors, right? So that's one theory. That is type 2A. Right? In type 2B, you choose chiral on both sectors, right? Then the fermions will be both carry positive chirality. Right? The kind of fermions you get from the ground state will all both carry positive chirality. That's why type 2B is what is known as chiral theory, right? It has spinors in the chiral representation, whereas type 2A has spinors in non-chiral representation. Half of them are left chiral, half of them are right chiral.
Once you have done all these with Fermionic sectors, I mean, then the Ramon sector is not, I mean, already fixed because.
Yeah. Then once you have fixed separately what to do in the Ramon sector on the left and Ramon sector on the right, then the Ramon sector, you don't have any more choice, right? You cannot change the rules in the Ramon sector from NSR sector, right? Once you have chosen a particular rule for doing what you want to do in the say right moving Ramon sector, right? Then you have to follow the same rule in NSR and RR. Okay? So this basically fixes the RR spectrum, right, in 2A and 2B theory, and they are different, right? Because in the 2A theory, the RR spectrum will be bispinor with both spinors same chirality. Right? In 2A theory, it will be bispinor, but one spinor with positive chirality, the other one in negative chirality. So these bispinors are actually bosonic fields, right? Because they are transformed in the usual representation of Lorentz group, right? Not spinor representation. But they have different tensorial structure.
Like I have to see the decomposition, like 16 plus 16 prime will give me
16 times 16 prime. 16 times 16 prime. We will another decomposition, right?
one will appear in type, the other will.
Exactly. But 16 prime times 16 prime will give the same decomposition as 16 times 16. Right? That's why you don't get 4 different theories. You get the 4 you can say you get 4 different theories, but they are trivial, right? Type 2B theory with both spinors positive chirality and type 2B theory with both spinors negative chirality are really equivalent theories. Right? You don't get it's basically related by parity transformation, right?
At the group level, it's same, right? 16 cross 16 and 16 prime cross 16 prime is the same, right?
Yeah, it will give the same decomposition, exactly. Okay, so I think I'll stop here and continue next time. Okay? So next time we'll learn how to impose the ln and gn conditions on this. Yes.
Is it not possible to impose R and NS mixed condition depending on the mu level
You can, it will break Lorentz invariance
in the space?
in the space time.
In the tangle.
Yeah.
Manifestly, you're saying it like explicitly.
Yeah, because if you do mixed, right, then you cannot rotate in the mu coordinate, right?
But even it will break the Lorentz symmetry.
Yeah, it will break the Lorentz symmetry.
When I'm doing open strings, I'm also manifestly breaking some.
Yeah.